Hello everyone, my name is Zhenrong and I'm a bachelor student at ETH Zurich. Today I'm excited to share our work on blaster, characterizing the blast radius of Rowhammer. To begin, let me provide a brief overview. Previous studies have shown that DRAM devices with target row refresh are still vulnerable to Rowhammer attacks. Unfortunately, the problem becomes even worse with the increasing blast radius of a single aggressor. Rowhammer can affect victim rows located further away from the aggressor row. In our study, we introduced blaster patterns, which involve utilizing up to 8 aggressor rows in the hammering process. We investigate how multiple aggressors affect DDR4 DIMMs obtained from 3 different DRAM vendors. Our experimental findings demonstrate that far aggressors can increase the likelihood of triggering a bit flip. Additionally, we discovered that far aggressors decrease the number of activations required for the near aggressors. Before delving deeper into the details of blaster patterns, let me provide a brief summary of DRAM organization and Rowhammer. A DIMM, or a RAM stick, consists of multiple DRAM chips, each of which contains several DRAM banks. Now within a DRAM bank, we have multiple DRAM subarrays which are separated from one another by row buffers. Each DRAM subarray can be further divided into smaller units known as DRAM mats. These mats consist of grid-like arrangement of DRAM cells. Rowhammer is a vulnerability in DRAM that occurs when a specific row is repeatedly accessed, known as the aggressor row. If the aggressor row is repeatedly activated and pre-charged, its word line voltage toggles, which causes interference in the neighboring cells. This interference leads to the accelerated charge leakage in the cells of nearby rows. Ultimately, this results in the victim row being unable to retain data until the next refresh operation, causing bit flips. Initially, the Rowhammer study used single-sided patterns, where a single aggressor was activated and the adjacent rows above and below it were the victims. This is known as the single-sided pattern. Subsequent studies have revealed that the underlying mechanism of Rowhammer, which is charge leakage, is amplified if the victim row is sandwiched between the aggressor rows. This is referred to as a double-sided pattern. More recently, half-double patterns have been introduced. These patterns involve activating not only the 2 near aggressor rows, but also far aggressor rows located 2 rows away from the victim. We see that an aggressor can physically impact victim rows that are 2 rows away. Previous studies have explored the spatiality of aggressor rows in Rowhammer attacks. However, these studies mainly concentrated on LPDDR4X DRAM and did not extensively cover DDR4 DRAM devices from various manufacturers. Our objective is to investigate whether the half-double effect is present in DDR4 DRAM devices and if it is similarly strong. Consequently, we pose the following research question. To what extent do half-double patterns affect existing DDR4 DRAM devices? Before answering the question, let me shortly introduce the platform and setup we used. An off-the-shelf consumer CPU prohibits us from having fine-grained control over the exact command sent. To overcome this challenge, we used the FPGA-based DRAM testing infrastructure known as DRAM Bender. This platform allows us to exercise precise control over the DDR4 commands directed to the module. It enables us to bypass CPU caches for repeated row accesses and conduct experiments without the interference of Rowhammer mitigation or DRAM refresh. In total, we evaluate 3 DDR4 UDIMMs obtained from 3 different DRAM vendors, SK Hynix, Micron, and Samsung. To investigate the impact of far aggressors, we need to isolate the effect of near aggressors from those located further away. In other words, we want to ensure that the near aggressors alone do not cause any bit flips. To achieve this, we define HC star as the maximum number of hammer count with no bit flips. When the near aggressors are hammered HC star times, no bit flips occur in the victim row. In subsequent experiments, we bound the number of activations to the near aggressors by a fraction of HC star, which enables us to differentiate the effects caused by more distant aggressors. Now, let's take a look at the results. In a single-sided case, we have two aggressors, a near aggressor R1 and a far aggressor R2. The near aggressor is hammer ratio 1 times AC star times, and after each activation of R1, the far aggressor R2 is activated ratio 2 times. The sequence is visually depicted here. Each time R1 is activated, R2 is activated, let's say, for 4 times, meaning ratio 2 equals 4. We repeat this process AC star times ratio 1 times. To understand the impact of these activations, we created a heat map that displays the probability of triggering a bit flip, while varying ratio 1 and ratio 2. The heat map's darkness represents the probability, with darker shades indicating higher probabilities. The x-axis represents the variation in ratio 2, while the y-axis represents the variation in ratio 1. The box values show patterns that are less than 64 milliseconds, respecting the standard refresh window. For instance, if we set ratio 1 to 1 and ratio 2 to 0, it means that only the near aggressor R1 is hammered AC star times, and R2 is hammered 0 times. As introduced in the previous slide, this is insufficient to trigger a bit flip, resulting in a probability of 0. However, while we increase the hammer count of R2 by varying ratio 2, let's say to 4, we observe an increase in the bit flip probability. For the results from other vendors, we kindly refer you to the paper. Our observation indicates that the probability to trigger a bit flip increases with higher ratio 2. Previous research has also indicated that the blast radius of an aggressor has expanded. As shown in the figure, if an aggressor can affect victim rows located 4 rows away, we say the aggressor row has a blast radius of 4 or a blast diameter of 8. To develop secure mitigations, it is crucial to investigate the effects across a wider range of rows. To address this, we introduce a new class of patterns named blaster, which goes beyond the limitation of distance to aggressors. Blaster patterns involve multiple aggressor rows positioned at various distances from the victim row. This leads us to the following research question: what is the effect of blaster patterns? In our work, we systematically examined the impact of far aggressor rows. Including multiple aggressors in blaster patterns creates a large design space. We seek to determine how do varying activation ratios affect the victim row. We systematically explore the parameter space of blaster by varying the overall amount of activations and the distribution of activations to each aggressor. The figure on the right shows the visual representation of our notation for the row arrangement. The victim is positioned in the middle, while aggressor rows above and below it. In general, we refer to the aggressor rows adjacent to the victim as near aggressors, while those at greater distances are referred to as far aggressors. Now, let's move on to the results of blaster patterns, including distance 3 aggressor rows. In these experiments, we not only activated distance 1 and distance 2 aggressors, but also included distance 3 aggressors. We used ratio 3 to measure the number of activations to aggressor R3 in each iteration. The heat map on the left corresponds to the half-double pattern, where ratio 3 is set to 0. This means that the distance 3 aggressor is not hammered, and only distance 1 and distance 2 aggressors are activated. On its right, we have the updated heat map that shows the result when distance 3 aggressors are activated 8 times in each iteration. Ratio 3 equals 8. In this case, we observe a clear increase in the bit flip probability by up to 50%. Additionally, by incorporating distance 2 and distance 3 aggressors, we were able to reduce the number of activations to near aggressor R1 by 30%. Ratio 1 corresponds to 0.7. In other words, we obtained a 30% discount on the near aggressor. To summarize our findings, we have 2 important observations. Bit flip probability grows by up to 50% by incorporating both aggressor R2 and R3, and activations of near aggressor R1 can be further reduced by 30%. Ratio 1 equals 0.7. Now, let's move on to the double-sided case, where we introduce aggressors from the above as well. Here, we observe a clear increase in the bit flip probability while incorporating distinct 3 aggressors. We have 6 aggressors in our hands now. Do we need to utilize all of them? The answer turned out to be no. Interestingly, we notice that the increase is possible when ratio 2 is set to 0, meaning that distance 2 aggressors are not activated. We make the following observation. The effect of aggressor R3 does not require aggressor R2 to propagate to the victim row. Finally, let's take a look at the impact of distance 4 aggressors. Our investigation is represented by the line plot. On the x-axis, we vary the number of activation of aggressor R4. The blue line corresponds to a scenario where R1 is hammered AC start times, and we vary the number of activations of aggressor R4 as indicated on the x-axis. In this case, R2 and R3 are not hammered. We observe a significant increase in the probability of bit flips as the number of activations to R4 increases. On the other hand, the orange line represents a scenario where R1 is hammered 0.9 times AC start times, where R2 and R3 are hammered 4 times in each iteration. Similarly, we vary the number of activations to R4. However, this time, the increase in bit flip probability is not as significant as compared to the previous scenario. We make the following observation. The probability of inducing bit flips mostly increases in patterns where ratio 1 is high. In conclusion, we introduce blaster patterns, which involve multiple aggressors positioned at various distances from the victim row. We characterize the impact of blaster patterns on 24 commodity DRAM chips obtained from 3 major DRAM vendors. We showed that future Rowhammer mitigations should consider aggressors up to 4 rows apart from a potential victim row. Thank you for your attention.